These are the notes for AP Calculus on the topic of parametric formulas with the graphing calculator. So on this one it says for time greater than or equal to 0, which is usually, we're only considering non-negative time. So our particle is moving along a curve, so its position is x of t, y of t. But notice we're not given those equations for the position function. Instead, it says at time 1, the particle is at this position, 3, 5. And we know dx dt and dy dt, what they're equal to. So dx dt, that's really giving us the horizontal velocity. This is the derivative of the x-coordinate position. And similarly, dy dt, that represents the vertical velocity, since that's the derivative of the position, the y-coordinate of the position function. So there's two components to velocity, because we're looking in two dimensions with these parametric functions. And then it says, for part A, is the horizontal movement of the particle to the left or to the right at time 1. Explain your answer. All right, so horizontal movement, moving left to right, is going to be determined by dx dt. Whereas if it asks for vertical movement, up or down, then it would be determined by dy dt. So let's go ahead and enter both of these in our calculator first and see how we can put it in parametric mode. So let's start with 84. And so the first thing, to switch it to parametric mode, is hit the mode button. And then normally it's on regular function mode. We'll still use that on these parametric ones sometimes. But we're going to switch it to parametric mode right there. So pars for parametric. And second quit out of there. And then when you go to y equals, it's going to look a little different. So here we're going to use x1 of t, that's going to be dx dt. Just remember, in this case it represents the derivative, and y1 of t is dy dt. So they don't represent the position, they represent the derivatives of the position, the two components of velocity. But we'll still enter them in here. So we'll have the square root of, now when you press the xt theta n button, it's going to put t, since it's in parametric mode, plus 3. Whoops, got the plus sign there. Close parentheses on that, square root, and then divided by e to the t. So second e to the t power. And then for dy dt, we'll enter in cosine of t. Okay, and we'll come back to these here. And now let's go to the Inspire. See how you do that here. So new document, add graphs. Now it starts off in normal function mode, f1 of x. To switch that, you go menu, and then number 3, or whichever it's listed as graph entry, and then go down to the little one that says parametric. And then it'll ask you to enter in x1 of t and y1 of t. So here we're going to put in the fraction notation here next to the 9. For this one, and this is the square root. Here you just use the t down right here, this is t, plus 3. Divided by e to the t, and y1 of t is cosine of t. And this is giving us the interval here of time. We'll come back to here. Let's look and see what it says here. It says time greater than or equal to 0, so we don't have a specific time as our upper limit on this one. Sometimes you do. So we'll just leave that in there. The default right now is, you can see, about 2 pi, 6.28. And let's go ahead and set up what this is going to be on paper, what we're going to do, now that we have them entered in both calculators. So horizontal movement, again, deals with dx dt. And we want it specifically at time 1. So we really, since we already have the derivative, the horizontal velocity would just be dx dt specifically at t equals 1. Now, if this was position, we'd have to use the derivative component of our graphing calculator to find the derivative and then plug in 1. But this is already in our calculator, right, as the derivative, as x1 of t. So all we have to do, go back to the 84 first, is go bars, and then y variables, and then instead of number 1 function, we're going to use number 2 parametric. In this case, we want x1 of t. That was our horizontal velocity, so x1. And we just want to plug in 1 to that. So you just put parentheses 1, close parentheses. And we get 7 point, or I think it was 0.7, wasn't it? Yeah, 0.736. And the key is that that's greater than 0. Meaning it's moving to the right. If it was less than 0, it's moving to the left. So we write it down, and I can show you how you do this on the Inspire. So we can say at t equals 1. We're not giving any units per time on this one. Sometimes you are, so we're not. So we can say that the particle is moving to the right, and your reason would be since it says explain your answer, dx dt, specifically at t equals 1, is greater than 0. And then on the Inspire, how you get that same answer here is just finish entering this in. Again, it's not the graph of the position here, it's the graph of the 2 derivatives. And then you just go doc, insert, calculator, and then you can access the variable. In this case, we want x1 of 1. Enter, we get the same answer. All right, let's take a look at part B. It says find the x-coordinate of the particle's position at time 5. So we don't have the exact position function. Otherwise, we would just substitute 5 into x of t, but we don't have that. But what we do know, notice, is at time 1, we know the x-coordinate right here is 3. So you can set it up like an initial plus change problem. We're trying to find x of 5, position time 5. So the initial here that we know is, I'm going to first just write it as x of 1 because we know what it is at time 1, even though we know that's equal to 3 here, plus the change, remember, is represented by the definite interval. In this case, from wherever your initial is goes as your lower limit to wherever you're trying to find it is 5. We'll figure out how much is the change from time 1 to time 5 of the derivative of x, and that's what the x dt is. So we put in the square root of t plus 3 over e to the t dt. And then this is where our calculator can evaluate this for us. Again, x1, we can see the x-coordinate at time 1 is 3. So let's go ahead and see how we put this in both calculators here. So back to the 84, it would be 3 plus, and then math. Number 9, again, function integrate. And what we're integrating, bars, y variables, and then go down to number 2 parametric is x1, comma. Now when you hit this xt theta in button in parametric one, it's going to say t, comma. Instead of x, you just hit the lower limit is 1, comma, the upper limit is 5. And we get 3.799. So that's the x-coordinate at time 5. And let's look look at how we do the same thing on the Inspire. And right here, you would just go 3 plus, that was our initial. And then integral is right here, next to 9. Lower limit is 1, upper limit 5, and then it's right here, x1 of t, is our variable, dt. You get the same answer. Alright, now let's go on to the next part of this one. Part C says find the speed of the particle at time 4. So remember speed, go back and look at our definition here. Remember speed, it's coming from the Pythagorean theorem, it's the square root of dx dt or x prime of t squared plus y dy dt or y prime squared. And we want a specific time here. So it's going to look more like this notation here. So it's going to be the square root of dx dt, specifically at t equals 4, squared plus dy dt at t equals 4 squared. And let's see how we put this in both calculators to evaluate it. So on the 84, we have the square root first. And then we get open parentheses to square this. So open parentheses there, and then we need x1 is what this one is. So go over to y variables, number 2 parametric. And remember, we want to evaluate it at 4. So parentheses 4, close parentheses on the x1. And then we need to close parentheses so we can square that. Plus, and the same thing here, open parentheses, vars, y variables, and then parametric again. And now we need y1. And then parentheses, again we're substituting 4, close parentheses so we can square it. And then close parentheses on the square root. And we get 0.655. Again, we don't have any units here. It could be meters per second, inches per minute. We just don't know what it is, so we don't have to put any units. And now let's look at the Inspire, how we do the same thing. So square root, or x1, whoops, I forgot the open parentheses, let's go back here. Open parentheses, x1 of 4, squared, plus, open parentheses, y1 of 4, squared. We get the same answer. Alright, let's take a look at the next part here. Next one says find the acceleration vector at time 7. So, just like the velocity has 2 components, so does acceleration. So what we really want is the derivative of the velocity here to get acceleration. There's 2 components. So the way you'd write that is squared x dt squared. But again, we want it specifically at time 7. Comma, the same thing, d squared y dt squared, specifically at t equals 7. So if this had been without calculator problem, we'd have to take the derivative by hand and then plug in 7, which you still could do here. You could take the derivative of this one using the quotient rule here, chain rule, and the derivative of this one's pretty easy here. Or you can use your calculator to save you some time. So since this is a graphical calculator problem, let's go ahead and use our calculator on each of these. So for the x-coordinate, so 84 again. So use the derivative function again, so math, numerical derivative. And then we want to take the derivative as x1 because that was already dx dt to get the second derivative. So then parametric x1, and then the notation of comma, your variable is t, comma, we're plugging in 7. And we get to the thousandth place, negative 0.003. And then again on the Inspire derivative here, you can there's different ways, but probably these ways: you go menu, calculus, derivative at a point. The variable here is t. We want the first derivative because we already have the first derivative in there. So the first derivative of the first derivative will give us the second derivative. The value we're going to plug in is 7. And what we want the derivative of is x1 of t. The same answer. And then for the other one, back to 84. Now to save yourself some time, notice that we want the exact same thing except for we want to take the derivative of y, so you can go second entry. And then all you have to replace here is instead of x1 of t, just go vars, y variables, parametric, and go y1 t. Otherwise everything's the same. And we get negative 0.567, 5657 I should say. The acceleration of the y coordinate, or the vertical acceleration, you could call it. And again, same thing on the Inspire. And one way to do it, you can go Control C, Control V, Control V to paste. And then again, all we have to change here is this one. We want it to be Y1 instead. Highlight that whole thing. Alright, and let's look at the last part of this one. It says find the distance traveled. Sometimes it says the length of the path, distance traveled. Either way, it's the same format from 3 to 8. So whenever you want the total distance, you're integrating speed. So in this case, the integral would be from 3 to 8. And we integrate speed. The difference is the speed here was at a specific time 4. Here we don't plug in a specific time because we want to be able to use all the times from 3 to 8. So we just leave it without plugging anything as dx dt squared, which you can write in what it is, or just leave it like this, plus dy dt squared. Times dt. Alright, and let's work this out on both calculators here. So on the 84, again, we want to integrate, so you'll math number 9, function integrate. First we get the square root. And then we open parentheses, and we got a square dx dt, which is x1. So close parentheses, squared, and then plus, open parentheses, y1 squared, and then close parentheses on the square root, comma, variable t, comma, lower limit 3, comma, upper limit 8. Sometimes with the square roots you have to wait a little while on the calculator to approximate the integral, I've noticed. So just be patient, I'll eventually give us the answer. There it is, 3.159. The units, whatever the measurements are. And on the Inspire, just go the integral here from 3 to 8. square root, then open parentheses, x1 of t squared plus open parentheses y1 t squared, and then put the t right here for dt, and you get the same answer. Alright, so let's take a look at one more with the graphing calculator, and this one asks for some different things here. So let's go ahead and enter these in both calculators here. So again, notice we're given x and y, t and y are not explicitly given, and we're given dx dt and dy dt, and we're told at time 0, this is basically saying the x coordinate is 1 and the y coordinate at time 0 is 3. It's negative 3, I should say, okay? Which is written a little differently, but really the same information as the last problem when it was telling us that at time 1, the x coordinate was 3 and the y coordinate was 5. Just written a little differently. Alright, so now for part A, we want the tangent line at time 1. So let's go ahead and put these both in our calculators first. So 84, we'll go back to y equals, clear these two out. And again, notice these are already the derivatives. So the graph we're getting here is not the graph of the position, it's the graphs of the two velocity functions. So it's not really showing you the graph of the path of the particle here. But to get that, you'd have to have x of t and y of t, the original ones. So we've got t squared minus 6t plus 8. Oops. And then we've got t, and then e to the t minus 2, close parentheses on the exponent, and then minus 1. Put that in now. And then on the inspire, let's go back here and tab. Now you can leave them in there if you want, or I'm just going to delete them out here since we're done with this problem. And we've got t squared minus 6t plus 8, and t, and be careful on the inspire. It might be okay just putting it here, but it's better off, you're better off putting time so the calculator knows for sure you're wanting to multiply. The inspire doesn't always recognize those when they're written right next to each other, especially with trig functions as being wanting to multiply. And then the exponent here is t minus 2. And hit the right arrow to get out of the exponent, and then minus 1. Alright, then let's go to what it's asking for. So it's asking for the tangent line at time 1. So remember, for the tangent line, you need two things. You need your point of tangency and the slope. So the slope, remember, is still dy dx, which remember, for parametric ones, is dy dt divided by dx dt. The difference here is we don't need the whole equation, in which case we would just put these two in. We need them specifically at time 1. So, if we want the derivative specifically at time 1, we need dy dt at time 1 divided by dx dt at time 1. Since we're not interested in the equation for dy dx, in this case, just the slope specifically at time 1. So let's answer this in our calculator. We've got 84 here. So we would just enter in, this was y1t, so vars, y variables, parametric. And then number 2, y1t, and then we want to plug in 1. And then divided by variables y variable is parametric, and then it would be x1 is our dx dt we entered in, parentheses 1. And we get negative 0.211. That's our slope of our tangent line. And again on the inspire, back to here, you would just go variables y1 of 1, you can put in the fraction here, and then variables x1 of 1. Get the same thing. Alright, so now the other thing we need beside the slope is the point of tangent. Now if the time was 0, we would already have the point of tangent here is 1 and negative 3. But it's not, it's time 1. So, kind of like we did with the last problem, we have to figure out the x and y coordinates, but this time separately as initial plus change problems. So, if we want to find x of 1, it's going to be the initial which is x of 0, plus the change, the integral from 0 to 1 in this case, 0 is wherever initial is, what we're looking for is a 1, of dy dt. I'm sorry, dx dt. And you can write it in here like this, or you can put dx dt, either way. And if you write it as dx dt, you can kind of see why this is going to work here. Because, yeah, the dt's would cancel out, and then you're integrating x, which is why it's giving you the change in the x coordinate. We can set it up like that. And we know our initial position for the x coordinate is 1. So this would be 1 plus math number 9, function integrate, and we want to integrate variables, y variables, parametric, x1, comma, t is our lower limit, sorry, t is our variable, comma, 0 is our lower limit, comma, 1 is our upper limit. And we get 6.333, which is really 6 1/3. Because you can see this one wouldn't be that hard to integrate by hand. And then on the inspire, do the same thing. So 1 plus integral from 0 to 1 x1 of t dt. And now let's go ahead and set up the initial plus change for the y coordinate. So for y of 1, it would be, the initial would be again y of 0, which we're told is negative 3 right here, plus the change, again would be from 0, our initial, so we're looking forward to time 1, time is a change from 0 to 1, dy dt. And then dt. So again, you can write it in here or just write it as dy dt, either way. Again, you can see the dt's would cancel, and that's how it's going to tell us how much the y coordinate changes there. So we can enter this one negative 3. If you want, you can see there's a little time. It's very similar to this one, so we can go second entry. And then just change this negative, and then the second insert 3, so it's negative 3 plus, and then everything's the same except for this one we want it to be y1 of t. So we're on top of that, vars, y variables, oops, sorry. We want vars, y variables parametric, y1 of t. 0 to 1. So we get negative 3.865 if we run it. So there's our y coordinate. And again on the Inspire, and if you want to copy and paste you can. I'm not sure how much time it saves here really, but you could. And just change this to a negative 3. And then just delete x1 and put in y1 and t. So now that's our point of tangency. Just took a little longer to find the x and y coordinates. So the point of tangency is 6.333, negative 3.865. And we have our slope here as negative 0.211. So finally our tangent line would be y minus the y coordinate, which will make it plus 3.865 equals our slope, which was negative 0.211 times x minus the x coordinate was 6.333. So it took a little more work to get the tangent line on this one, because we had to use initial plus change for both the x and y coordinate. Now remember the last problem asked about the horizontal movement. This one asks is the vertical movement upward or downward at time 1. So the vertical movement is determined by dy dt, the vertical velocity right here. So all we need to figure out is dy dt, specifically at time 1. And remember that's already in our calculator. So we can just substitute that in. So we get negative 0.632. And notice that's less than 0, so that means it's moving downward. Let's put that in our Inspire so we get the same thing. So in Inspire, just go bar y1 of 1. Okay. So we can say at t equals 1, the particle is moving downward or down. Let's word it the same way the problem does. Since our reason is that dy dt, the vertical velocity, specifically at t equals 1, is less than 0. Alright, let's take a look at a few more with this problem, but a little bit different. So this one says for part C, find the time when the tangent line, the path of the particle, is horizontal. So we want to find time when it's horizontal here. So if we want the tangent line to be horizontal, remember what we saw before, that means the derivative, dy dx equals 0. But remember, dy dx, if we look back here, if we want it to be 0, that means the numerator is 0. So that means we really need the numerator, which is dy dt, equals 0. And notice this time it gives us an interval, 0 to 5. Okay? So what we really want to enter in is dy dt equal to 0, so that's our t e to the t minus 2 minus 1 equal to 0. But as far as I know, in the parametric mode, it won't solve this for us, but it will in regular function mode. So I'm going to write that down here. Enter in regular function mode. I'll show you what I think is the quickest way to do that, to solve this. So let's look at the 84 first. So go to mode here, and let's switch it back to regular function mode. And then for y equals, you can do one of two things. You can type this whole thing in using x instead of t and find the zeros of that. Or an easier way of doing that, since it's already in your calculator, just go vars, y variable is parametric. And we already have this dy dt as y1, remember? And all we have to do to change the variable to x, just like you would if you wanted to plug in 3 for t, you'd have parentheses 3, now you put parentheses x. And then all it does is replace these t's with x, so it's the same function, just with x in there. And then we can go to window size, and we want to just look between 0 and 5. Since x is like our t here, so we get x minimum 0, x maximum 5. And you just want to make your y min and max maybe just so you can see where it's equal to 0, so make the y min something negative. I'll just make it negative 5, and the y max 5. And then you can go second calc, and we're going to use the one that says zeros or roots. You see the graph of it, you see it's 0 right there. And that's it. There's nowhere else in this interval that is 0. So left bound, and move the cursor to the left of it, or Tyson data to the left of it, enter. Right bound to the right of it, enter, and yes. So, let's find the time. That's our first objective here. It's at 1.557. So that's our first answer for when the tangent line is horizontal. But what we want to figure out is the direction of the motion particle towards the left or toward the right at that time. So, because we need to use this time, let's store it in our calculator. I'll call it A, 1.557. I'll store it, and then we'll see how we get the same thing on the Inspire. So second quit, again, store alpha A, enter. And then we'll go to the Inspire and figure out the same thing before we do the second part of this problem. So for the Inspire again, all you have to do is go dock, insert, graph. So you have another graph. So this one's going to stay the parametric one. So they're still in our calculator. And then 1.3, we'll just leave this in regular function mode. And again, you can just enter in var. It was y, so y1, and then just put up x. So it just replaces all those t's with x's, basically. And then you can already see it right there. But you technically would change your window size here. Since we're looking just from 0 to 5. And as long as 0 is in here, you'll be able to see it. So we know that's the only interval we're looking for, it's 0. And then you go menu, analyze graph, 0. Lower bound, click the dot line to the left, upper bound to the right. And there it is, the same value. And then to store it, var, store, A, enter. Alright, let's go back to the second part of this now. So if we want to know if it's moving left or right, then we have to use dx dt. And we want to know at this time. So we just need to find what is dx dt specifically at, here I can just write it as t equals a since I defined it right now. And since that's already in our calculator, all we have to do is put that in for both of them. So that's var y variable. You can have in either mode here when you're doing this. Parametric, x1 of t, and we want to plug in a, so alpha a. And we get 1.082, we got it. The kids, if that's greater than 0, so that means it's moving to the right. So we can say that t equals a. So to give a reason for answer, the particle is moving to the right. And then your justification would be since dx dt at t equals a is greater than 0. let's do the same thing on the Inspire here real quick. So for the Inspire, again, just go back to 1.2 right here, and then we would just enter in, we already stored as A, so var x1 of A. All right, then the last part of this one is similar, except now it says find the time from 0 to 3, so the interval gets a little smaller here, when the tangent line is vertical. So that means dy dx is undefined. In order for the derivative to be undefined, rather than the numerator being 0, where it makes it 0, the denominator has to be 0. Remember, the denominator comes from dx dt. So when you're looking for vertical tangent lines, you're really just you're setting dx dt equal to 0. So our dx dt here was t squared minus 6t plus 8. Okay. Now this one, you can actually solve by hand, right? You could use your calculator just like we did the other one and put in x1 of x in the regular function mode. Or, you can see you can just factor this into t minus 2 and t minus 4. So you get 2 times initially, t equals 2 and t equals 4, but notice 4 is not in the interval. So we're going to cross out time 4. So the only one in the interval 0 to 3 is time 2. So that part we didn't need our calculator for. And then we want to substitute that into the second part of this asks is the direction of the motion particle upward or downward at that time. So at time 2 is moving up or down, then we need dy dt. So we need to know what is dy dt, specifically at t equals 2. Again, if we needed to use our calculator like we did this one that's harder to solve, we could have in the same way, but sometimes it's easier and faster just to solve it by hand. It just depends on what the equation is. So, again, using the 84, you would go variables, y variables parametric, y2, sorry, y1, and then put in time 2. And get 1. So that's greater than 0, so that means it's moving up. So we can say at t equals 2, the particle is moving, let's say up or upward is how it words here. And your reason would be since dy dt at t equals 2 is greater than 0. And finally, just review how we find that value on the Inspire. So you just go var y1 of 2 and get the same answer 1. And that concludes the notes for AP Calculus on the topics of parametric functions using the graphing calculator.